Welcome, Kyriakos, and also thank you for giving a talk to us today. There's a small audience today. I don't know why actually, but there are a few people online also, so that's nice. So welcome everybody, also online. So Kyriakos Vamvoudakis is the Dutton-Ducoffe Endowed Professor at the Guggenheim School of Aerospace Engineering in Georgia Tech. He got a PhD in 2011 at the University of Texas in Arlington, and spent time in Santa Barbara as a research scientist, and since 2016 at Georgia Tech. It's a subject which I think is, very interesting for us as complex systems and control. So we're really looking forward to the talk. Kyriakos, the floor is yours. We don't hear it.
Sorry, we cannot hear you.
You can hear me?
Yeah, we can hear you.
Yeah.
Yes.
Okay. So I was saying thank you very much for the invitation. It's a pleasure, and thank you for joining the talk. My talk title is Data-Driven Sensor and Actuator Selection for Intelligent Complex Adaptive Systems. So, of course, complex adaptive systems, they're a form of cyber-physical systems. So let me give you a background about what a cyber-physical system is, which actually my lab is called at Georgia Tech, is called Intelligent Cyber-Physical Systems. And we work a lot on different components of cyber-physical systems. So what is interesting about cyber-physical systems is that they're highly complex and interconnected. And as the word says, it's a combination of physical, computational, and communication components. And there is applications all over from different components, aerospace, military, healthcare, smart grids, autonomous drivings, and so on and so forth. Of course, the time that we want to make them more adaptive, we incorporate also more learning components in them. So this actually increases the complexity and the uncertainty across all layers, which again incorporates layers of physical, computational, and communication layers. And our work tries to bring ideas from data-driven control, and we want to see how we can intelligently place actuators and sensors in such a system with less information about the model, while we also let it be adaptive to change that can happen, and also resilient to different adversarial components that can enter the system as the system becomes more intelligent. So, before we see how we can actually select actuators and sensors, so I'm sure all of you're familiar what is an actuator. Actually, it's a device that you can see on the right that can implement a control input. In other words, it is every column in a matrix B. For example, if we take a linear system, which is, for example, x dot equals, say, x plus bu, every column of the B matrix is actually an actuator, okay? So why we want to actually work on actuator selection in complex adaptive systems? Because we want to improve controllability, we want to be resilient to several faults and failures, and we want, of course, to improve energy efficiency. So this is a small motivation of why. And of course, actuator and sensor selection are dual to each other. So you can think that sensor is a row of a C matrix, and then you want to improve observability, but while also being resilient to faults and failures and so on and so forth. So every time I talk about one, you will also see the dual. Okay, so up to now, if we want to make complex adaptive systems, we want to make our algorithms depend less on models. So in other words, we want to have them completely data-driven and completely model-free. So up to now, every time you want to select your actuators to incorporate into your system, everything is tied to system models. But of course, in a cyber-physical system perspective, if we want to make them more intelligent and more adaptive, we don't know much about the system, or it might be inaccurate, or it might change over time. So we want our algorithms to be less dependent on our systems. And what I mean by the systems, I mean the physics of the system, so the dynamics of the system. Okay, so that's why we have been working on solutions that they are data driven, and then you will see how this can be achieved. So let's actually start motivating the problem and see how we can take a model based and make it model free. Okay, so I mean, as controls people, we work with dynamics. So let's say, for example, I have a linear system of x dot equals say x plus bu, okay, where x is the state, u is the control input, a is the drift dynamics matrix, and b is the input dynamics matrix. Again, you will see that everything that I will develop later will be model free, but I want to motivate based on the model first. And of course, we have worked also on nonlinear systems, but I want this presentation to be clean and show you how clean equations we can get. Okay, so as I said before, each column of this matrix B that's linear to the U is an actuator, okay? So in every B matrix, so we will have a B0 part and a B mathcal vita part. What this means, actually it's straightforward, is like we have already incorporated some actuators of this in the system, but we want to select some more to improve controllability, to improve resilience to faults, and so on and so forth. So every time you see B0 is actually the actuators that are already part of the system. And every time you see B mathcal vita are the actuators that need to be selected, okay? So, of course, we have freedom in only picking this B mathcal vita, okay? So I want to choose the best ones, put into the system, improve controllability, and so on and so forth, as you will see. Okay, so, but before we see, I mean, what does it mean in practice though, okay? So again, I have a pool of available actuators, and usually in a complex adaptive system or cyber-physical system, you have redundancy in everything you do, okay? For example, we have redundancy in your sensor, redundancy in your actuators. So if something goes bad, you want to put something else in, okay? So again, what does choose mean in our framework? So again, every time I say choose, it means that I have a pool of available actuators. Let's say I have n of them, okay? And I want to pick the best k of them to put them into the system, okay? So of course, I want to do that in a way to improve controllability, okay? So since I want to improve controllability, every time I see the word improve, it means that I want to maximize or minimize. So in our framework, we want to maximize controllability, okay? So, and of course, I have to find what I want to maximize. And also this cardinality B equals to K is because I want to pick the K best of them. Okay, so after we find, as you will see in a bit, this K, so then we set them into the choosable B and we incorporate into the system. Okay, so I told you that I will maximize controllability, but I didn't give you an equation yet for it. Okay, so this F mathcal vita will be quantifying the controllability. Okay, so let's say actually if we take a pure minimum energy control problem where I want to minimize U and pick it in this way, okay? This is a straightforward optimization problem, a minimum energy problem, okay? So as you will see that the more controllable systems, they have smaller optimal values, okay? And actually this has a straightforward solution, closed form solution, which is given by this guy over here. This is the optimal value. And of course you see this QTF that is inverted. Of course, every system that is controllable has this invertible, okay? So this is the controllability Gramian that we all have seen in several controls classes or in several papers, okay? So let's see how actually we can incorporate this controllability Gramian inside this optimization. Okay, so again, this controllability Gramian quantifies the efficiency of the B matrix, okay? So as you can expect, the larger Q is better, as small Q is worse, okay? So then let's actually choose this F of vita here to be the trace of the controllability Gramian, okay? So again, as of now, we have found that I want to optimize the trace of the controllability Gramian, and still my final time still remains free. Okay, and of course I want to do this optimization with respect that I have k actuators to choose. Okay, so of course, if I take my time to infinity, then my everything becomes an algebraic equation. There is no integrations. Okay, again, these are straightforward stuff for now. But in order for us to solve these equations in this framework, okay, so of course I want to have my A to be stable. Okay, but of course, I can always play by incorporating and moving my poles by incorporating this gamma, okay? And then I can move them, then I don't have to require that A is Hurwitz, okay? Oops. Okay, so let's recap. So what I want to do here is I want to maximize this trace Q, okay? Where Q will come from the solution of this Lyapunov equation. But of course, see, again, you see that in order for us to solve these problems, again, we require A and B, okay? So we still haven't done really anything yet. So we still want to provide a framework that solves all these equations in real time in a data-driven way without requiring any information about A and B, okay? So, so our work has done lots of stuff in reinforcement learning. So let's see actually how we can use learning methods from reinforcement learning, of course, to solve this Lyapunov equation that you saw before. Okay, so, but of course, the reinforcement learning methods that we use in control, they focus on the dual Lyapunov equation. So what I mean by dual is that the transposes appear in a different way, okay? So you will see why this can potentially be a problem. So again, we can actually have a theorem where we can solve this f of v, okay, and solve it in a closed form solution. But again, all these things are model free, and we still haven't found a solution up to now of how to do that. And then you will see how actually we can convert these Lyapunov equations that they are on the form not dealt before in RL to a form that we can deal with and solve them in a model-free framework. Okay, so again, we had our controllability grammar before, so now we actually have rewritten our optimization problem in this way, okay? So let's see actually how we can use reinforcement learning to express our cost with data, okay? Completely data-driven. And I will say that the main idea is pretty simple because this A transpose plus PA is almost the derivative of X, almost vaguely speaking about. So let's see what we can do. So every time that we want to do reinforcement learning, we want to have everything that we don't know in a component that we will approximate. We will call it a weight vector or the vector of unknowns. And then we will use everything else as a basis or activation functions to tune our weights. Okay. So for example, since this A transpose P plus PA is almost the derivative of X, so then the matrix P will satisfy these equations. Okay. Again, remember that I want to find this P if I knew the model. And since I don't know it, I just want to put it in a vectorized form. Okay. So I vectorize my matrix P. I put all the unknowns there. And then this is, you can think like an activation function, which is like different Kronecker products of the states and the control inputs that you put into the system. Again, for now, again, we have, and then this T that you see in here is actually, we will call it as the reinforcement horizon. So when you see this argument, these equations here, still you see that the B appears, but the A doesn't appear, okay? Let's see what we can do though. Okay, so This equation, we can still solve it offline, right? I can just do least squares, okay, collect enough data, and then I can find this vectorized P gamma, okay? But of course, I don't want to do stuff offline because I want to do complete learning-based frameworks that they don't even require any pre-training. Because, the beauty of control is that we have feedback. So it's not like we are doing open loop training and then we have to have a computer, we do pre-training and then we enforce it into our system. What we do in control is we have this beauty of feedback, and then I can improve always my control. So I don't need to do any pre-training, but everything happens in real time. So what you saw before, so if I move everything from the left-hand side, I can call it something like a temporal difference error, right? So if I force it, if I pick my tuning, if I tune my unknowns to make the temporal difference error 0, then I will solve it online. So what people in reinforcement learning do is that we define a square error, okay? So if, let's say you didn't have this squared here, so what you had, you want to move to, this will be called a temporal difference error, okay? So then I can do pure gradient descent on this one and then pick my vectorized P to take this error to 0, okay? So this is actually what I told you just now, okay? So, and then the other part that you see here is just a normalization to make things better. But again, this is pretty straightforward. What we do, we take a temporal difference error, we square it, and then we tune the unknown components with gradient descent. And of course, the sigma is a learning rate, okay? So now I can find the components of the unknown matrix P that you see over here, okay? And I can solve it without having any information about the system, as you can see here. Okay, so of course, everything we do is actually guaranteed with different theorems. So we actually prove that I can identify my ideal P given some precision of excitation conditions on the phi. So precision of excitation is I incorporate some noise into my control inputs to do exploitation that we want to do in learning, which is actually equal to doing precision of excitation in adaptive control, okay? Of course, we can also relax this precision of excitation by using previous data. But for now, let's focus on that one. Again, here we will be able to solve the problem that you see on the right-hand side, to find the P without information about the dynamics, and we do it online, okay? So let's see actually now how we can put everything together and do our actuator selection. So what we do here is we wait until the P converges, and of course the P converges in fixed time, and then select the best actuators, and I can place them either online or wait for them to do online, okay? So let's see actually how we can do that. So at any time instant tj, okay, I decide that I can choose our actuator selection by solving this problem, okay? So again, remember, this P hat can be solved from before. So every time I change my P, I change my actuators, okay? So these TJs are instants that my framework allows me to choose my actuators, okay? So again, here's actually a little pseudocode, how we can do it, okay? So we find the estimation of T, I sort my values, I choose my actuators, and then I put them back into the pool. Again, my B is time varying, right? And I let my B be time varying in this interval, okay? Okay, so of course, as I said, everything we do comes with guarantees and theorems, okay? So if we keep updating the actuator selection set, you will see every TJ. I will eventually find the optimal one, and it will be scheduled permanently in finite time. Given, of course, I have a guaranteed precision of excitation condition. Okay, so let's see actually how this can put everything together. Let's say I have this simulation example, okay? So again, remember that our framework doesn't require any information about the matrices, but I will show you and compare it to a framework if we had the system matrices. So this is actually a benchmark aircraft where I have available for me 7 available actuators, okay? So, and I want to choose 4. These are the parameters. I update every 10J. The sigma is how fast I tune my gradient descent, and my T is my reinforcement signal. Okay, so if I have the model and I want to do everything offline, so I know that the solution will be to pick 3, 4, 5, and 6. So from all these 7 available actuators, I have to pick 4. And the optimal ones to pick that and give me the best controllability will be 3, 4, 5, and 6. Okay? So again, this is the offline solution. Let's see actually how I can put everything together in the learning framework. So this, whatever you see on the left are the entries of the estimate of the p hat. Okay? You remember that I used learning, gradient descent, to find the components of this p hat. Okay? And you also see on the right the Frobenius norm of all of the p tilted, where you see that it goes to 0. So eventually I can I find the optimal solution. So then here you can see, here you can see that the black tells me which sensors have not been used, and the green are the ones that they have been used. So you see that the optimal one is 3, 4, 5, and 6, okay? Which is actually the same with my offline solution, okay? And again, all these things they're learned in real time. Again, a black tells me that the actuator is not used, and the green tells me that the actuator is used, okay? So again, 2, 3, 4, 5, and 6, which is the same with the offline solution. So, of course, we're also interested in a complex adaptive system. We're also interested into attack resilience, okay? What you have seen up to now, it takes into account only a minimum energy problem, okay, but doesn't take any potential possible actuation, faults, attack, or disturbances. So let's see how we can do that. Actually, this is pretty straightforward. We can actually reformulate as a game, okay? So we can have a zero-sum game or minimax solution where I find the minimum over U and the maximum over A. So A, it can potentially be a worst case attack, worst case disturbance, or anything unmodeled to my system. Okay, so now instead of quantifying the controllability that you saw before, I can quantify this game equations. So again, everything that we did before will be slightly changed, okay? So then instead of having the pure controllability, I have this game-based controllability Gramian, okay? And instead of learning the solution of to the controllability, I learn the solution to this game-based Gramian. And so again, all the analysis after that remains the same, okay? And so now, what we have done up to now in this presentation, we have developed the first model-free actuator selection algorithm, which is by design, all these actuator selections algorithms, they are very computationally expensive even to solve offline, okay? We have done, we selected our actuators that quantified both controllability and attack resilience, and of course, every model-free approach that we do, we want actually to show equivalence to the model-based approach. We don't want them, of course, to do any relaxation and so that, okay, yeah, this is a relaxed version. No. This model-free version converges to the model-based approaches. And we have published several papers on that. Okay, so let's see actually how we can even improve on that on other scenarios. So what you saw up to now was that controllability was measured on average, but not really across closed loop trajectories. So let's see what we can do now. Let's change a little bit the framework here. So let's say I have again my linear dynamics, okay? X is the state, V is any pre-specified control input, and A and G are unknown plant and input matrices. Okay, So of course, every time I want to map from actuators to controls, okay, as you remember from before, right, I can write this V that you see here as BU, where B is columns comprised of the actuators, and U can be actuator commands. Okay, so we will remember I told you about actuator redundancy. So a system is actuator redundant if I can pick a K larger than M, which is of course the rank of matrix B. Okay, so since we don't want to do over, as you see here, over on average, we want to do it a closed loop trajectories. So our problem now becomes an optimal control allocation, not an actuator placement anymore, but optimal control allocation. So this is another important problem in control. So let's see what actually is this problem. So again, I can, the actuator redundancy, I can always write any control input V with the proper choice of U. Remember, V is BU, okay? So what I want to do in the allocation problem is I want to choose my U with the minimum energy, okay? This is pretty straightforward here, as you see here, okay? And again, this W is just how much I weight each actuator, okay? Again, this has a clause from solution, pretty straightforward. Optimal solution is this one, and optimal cost is this one, okay? Nothing interesting up to now. But I want you to pay attention to this part over here, okay? Which is BW inverse B transpose, okay? So I can improve my cost by changing my B's and my W's, okay? And let's see what I can do on that one. So let's actually try to see how we can incorporate whatever I did before for the actuator selection, but I want to do that for optimal control allocation, okay? Again, in the same framework. Let's say I have a B, which is B1 and B2, and then if I add how many I have in B1 and B2, I will get K. Same things with before. Again, I have a fixed part and a choosable part, okay? So, same with before, okay? So I want to pick the choosable part so that the minimum energy that you saw before LB star T is minimized, okay? And I want to do that by changing also something that I have done before, okay? Again, this f of b is not the same with before, but it will be a little bit changed. So let's see what we can put here. Again, this f of b will quantify the minimum energy before I was quantifying controllability. Okay, so the matrix B1, that is the fixed part, okay, has full row rank, okay? This is to assure actuator redundancy, okay? Of course, this is not always necessary, but to make results cleaner here, I have to stick with it. Okay, let's actually start seeing in very simple steps how we can do that, okay? So case one, okay, agnostic actuator selection. Again, remember that my minimum energy that I found, right, the minimum energy, the cost, is given in this framework, okay? So, of course, if I don't know V, right, I cannot directly optimize that over all the B's. So I can do that, though, on average, okay? So my FV that I want to optimize will be the trace of the BW inverse B transpose. Of course, inverse, okay? So this is what I want to eventually optimize, okay? Because this minimum energy can still be optimized by choosing optimally this guy in the middle. Okay, so let's see now how we can do that, okay? So before, this one is more agnostic. Let's say actually if I knew V, what it will be. Suppose now that my V has an initial condition distribution known as Kx, okay? Of course, my A plus GK is Hurwitz, okay? So I can optimize this minimum energy directly over an infinite horizon, and I can choose my F that I want to optimize from before to be this one, okay? Again, remember, this is what if I knew the V. The before was if it was V agnostic, okay? So this is how we can optimize my FB and solve it. Okay, so again, since I want to eventually do learning in these model-based equations because I want to make the model free, I know how to solve equations that they come in a form of Lyapunov equations. So let's see actually what we can do. So I'm trying to solve this problem here with some Lyapunov equations. Okay, it was straightforward to derive that this problem can be solved by these two coupled Lyapunov equations. Okay, so then instead of solving QR, I can definitely solve also a trace of PV. Okay, of course, if I do the PV though, it is actually inefficient because this solves Lyapunov equations for all points in 2 to the power set of S. But using the trace of QR requires solving only one Lyapunov equation for Q. Okay? So let's see how we can do that. And of course, I want to do that in a model free. I don't want to have any offline solutions and solve all these equations by having information about the system. Okay, so again, recall now that I have picked my cost function to be this trace QR subject to these Lyapunov equations. Okay? Okay, so as you see, okay, the only part that has information about my dynamics is the second part. Remember that my system was x dot equals ax plus gv. Okay, so the only part that has information about the system dynamics is the second part. Okay, so but still also the cost depends on Q, which also depends on A and G through the Lyapunov equation. So let's see what we can do. Okay, we go back to our model-free formulations. Okay, but again, see that this Lyapunov equation, again, has the transposes on the wrong part. It's not really a Lyapunov, but it's a dual Lyapunov equation. So how we can solve this problem is I have to turn it into a nominal one, nominal Lyapunov equation, and after that, use the techniques I know in reinforcement learning to solve this problem. Okay, so actually, we can turn this dual Lyapunov equation by multiply left and right by Q inverse, and of course, Q is non-singular by our theorem that we had before. Okay, so again, I can change my Lyapunov equation by multiplying left and right with Q inverse to make it look like that. Now you see that the transposes, they appear in the correct places. Okay, so we can use any techniques that we can solve these equations in a model-free framework. Okay, and what we can do is we want to find first a gain that stabilizes the plant, A plus GK, and then I can perform any algorithm in a model-free framework such that ADP or off policy and so on and so forth. Okay, so we can solve these equations, either policy iteration, value iteration, and so on and so forth. So what you see here is a policy iteration, where, of course, in a policy iteration, I have to start with initial stabilizing policy, which is actually what it means is something that will make my closed loop matrix Hurwitz. Okay, and then I will iterate over some Lyapunov equations. Okay, of course, everything here also converges to the right equations. Okay. Oh, remember that because I changed my transposes, so now this minus sign has to appear here to be Hurwitz. Okay. So again, these actually equations, they're a little different from what you can see because this algebraic Riccati equation doesn't have a constant term. Remember that every time I want to solve, I have an algebraic Riccati equation, I have a constant term that comes from the Q, right? But here you don't see any constant terms here. Everything changes, right? Okay, so let's see actually how we can solve this. Again, every time we have something, a Lyapunov equation, which is actually the dual Lyapunov equation, I can always put the known and the unknowns into different vectors, and then eventually I can solve it with off-policy learning. Again, what you see here is nothing but I put the knowns and the unknowns in different vectors, and then eventually I have the unknowns, the knowns, and then some bases. Okay, and I can solve it with least squares, recursive least squares, gradient descent, or anything I want. Of course, in order for this to be solved, I want some assumptions on non-singularity. But again, all these things, they can become clear in a bit. Okay, of course, yeah, and I can prove that what I want, how big the dimensions I want to be full rank. Okay, so again, we can solve this given some least squares, okay? And I want to eventually find this Q inverse, okay? So this is it. So all this thing now that you see here is happening in real time, okay? So again, we prove also that not only the model-based framework is converging, but also the model-free framework will converge with different theorems. And then, of course, we prove that this algorithm that you see on the left is small disturbance input to state stable system. Okay, let's see how this can work. Let's say I have this eVTOL, which has 9 states and 5 high-level control inputs. Okay, and the available set of actuators, you can think it can be picked from this pool over here. Okay, so my initial actuator set is incorporating 1, 2, 3, 13, and 14. And I want to augment my initial actuator set with 6 more actuators. Okay, so let's see. Again, remember, my cost function was Q and R, right? My parameters and my behavioral control can be Kx plus eta. Oops. Okay, again, remember that I want to guarantee presence of excitation, and I can do that by incorporating some exploration noise. Okay, so what you see on the left is the norm of the states, and you can see that it goes to 0, it's very small. Also the norm of B, which is my control. And then here you see that eventually my off-policy learning was eventually converged to 0. So this is the error between Xi, which is the converged, and Q inverse, okay, the optimal one. So you see that converges to 0, and so eventually I converge to the right solution. Okay, so if I do that, then you will see that the optimal solution will be 2, 3, 4, 6, 7, and 11, okay, which actually agrees with our model-based techniques. Okay, so what we have done up to now is we designed and we found solutions to some computationally expensive, even offline frameworks, and we do them online in a model-free way, and we prove that it is small disturbance input state stable, and we're robust to input noise. And then we have published several papers on that. Okay, we have questions?
Thank you very much.
No, we have more. We have more.
Oh, you have more?
We have a little more. Yeah, I said I heard some noise. I was like, do we have any questions up now? We have a little more. Yeah. And so I told you that the actuators and the sensors, they are dual. So let's see actually how we can do sensors now, pretty brief. So, and again, we can deal also with discrete time systems. So let's say that I have this system here, xk plus 1, axk plus buk, and y is cxk. And again, now a, b, and c are unknown. Okay. So remember before I had columns for actuators, now I have each row of C is a sensor. Okay. And I want to choose some of the sensors in this C matrix. Okay. So of course I can choose a P prime, which is less than P. Okay. Again, P is the number of rows of C. Okay. So again, remember that choosing sensors is actually choosing rows of C. So in a similar framework with before, okay? So we want to make sure that I can find a way to pick these rows of C, okay? So this is a selection matrix. You can think this has 0 and 1s. And the final sensor matrix will be C tilted, which is this selection matrix multiplied with C. Again, vaguely speaking, we can find this E gamma to E gamma P, okay? So again, for us, we need to know an a priori set of sensors that will make our A S gamma C observable, okay? So let's see how similar way with before, how can I define the best sensors? Guess what? It's actually pretty straightforward because before I have observability, controllability. Now I have something that will be based on observability. And actually, I maximize this H2 norm of Y, okay? And again, I have this Lyapunov equations here, okay? So what I want to do is I want to optimize this this thing over here, this trace of CWCC transpose, okay? And I want to do that wherever I see the C matrix, I want to have this selection matrix to pick the appropriate rows of the C. That's why what you see here, right? In this S gamma star. And I want to do that only with input-output data, okay? In real time without any information about A, B, and C. So again, here, because I do sensor selection, I don't have full state feedback as before I had for the actuator selection, but I have only partial information about the state as because I have the output. So, but every time as you know, if I'm observable, I can always reconstruct my state using input-output history. Okay, and again, I can always write my state as a matrix multiplied with previous inputs, previous outputs. Okay, and I can always reconstruct my state based on that. Okay, and again, my M matrix has to do with controllability, observability, and a Toeplitz matrix. Okay. So let's see how actually I can make that work without information about A, B, and C. Okay. So I will denote the cost function, okay, as J infinity. This is the cost function on picking the S gammas, okay? And this is just some definitions of different data matrices. Again, I have my phi's that you will see what they are. I have my y's, and I have something that will serve as an activation function. Again, these are the output of the sensors to be evaluated, okay? And then again, here, this is some, I check the rank of this Y matrix to see when actually I can find this optimal solution for the selection matrices. Okay, so now I can design a greedy algorithm to find the best sensors in polynomial time using all the input-output data, okay? So I gather input, I evaluated the cost of the selection matrices, okay? I sort them in decreasing order, and then I update my C, okay? So let's see actually what we can do. And of course, we have proofs that all these things, they converge to the best set of sensors. Okay, so now, what I want to show is that these two things are dual, not only on the continuous time system that you see before, but also on the discrete time system, okay? So that's why I said here, same process can be used also to select actuators. So we can extend our optimization to find horizon observability metrics, or we can extend to optimization of volumetric observability measures. So let's see how some examples. Let's say I have this IEEE 39 bus test system, okay, where theta and theta dot are a rotor angle and frequency, and you'll see that in R10. And I have 20 state sensors, and my M is my inertia, this damping, and L is my Laplacian. And I want to discretize that with a time step of 0.2 to get my system edge in discrete time. So now, my initial set of sensors were 1, 3, 4, 6, and 8. Okay, so what I want to do is I want to augment this initial set with 7 more sensors out of all these things that I have here. Okay, remember my C here is 20 sensors. Okay, so again, let's since we can do volumetric costs, okay, we can also have a discount factor. And what you see on the left is the volumetric cost, estimate cost for all possible sensor sets. And then on the right, you will see that the estimation error is actually pretty small, okay? And the gritty algorithm found the optimal sensor set and told me that, okay, you have 1, 3, 4, 6, and 8, so you need to augment this with 2, 5, 7, 9, 10, 13, and 18 out of this set, okay? And again, we prove that this is actually the optimal set. Okay, so what we have done in this last part is that we utilized reinforcement learning for control, but we showed how we can use reinforcement learning to select sensor and actuators. We have used approaches that are applicable to continuous and discrete time systems with state and output feedback. And of course, we showed several simulations in large-scale systems. And with that, I would like to thank you all for being here, and I will be happy to answer any questions.
Thank you. Yeah, very interesting talk. Thank you very much. Any questions in the audience? Any questions online? Then I'll start with some questions. I mean, the main question I have here, is this now limited to linear systems in some way? Or so what happens if you have nonlinear systems? Can you solve this optimization locally then? And then get, you know, this sort of optimal sensors and actuators or not?
So, okay, so what I've shown here is that I want to solve the linear system because we actually know the solution and we can have closed form solutions. So of course we can do also nonlinear systems, but then this actually goes down to solving Hamilton-Jacobi-Bellman equations where we don't have a closed form solution, so we don't have a comparison. We know how to do it. We have actually things, but we don't know if we actually converge to something that is optimal or suboptimal, because we don't know exactly what is the closed form solution. But yeah, that's a very good question there.
Okay. And another question I had was on the Lyapunov solvers. I mean, what is usually done are low rank approximations of which can work to very large systems, which can work pretty well. Of course, then you need A, and here you want to do it model phi, but is there, in terms of the matrix, you could also reconstruct the matrix A from the dynamics, right? For instance, using dynamic mode decomposition or some other thing, and then solve the Lyapunov equation in a low rank approximation. Is that still very much computational expensive than what you do here in terms of reinforcement learning? Oh, we cannot hear you, sorry.
Yeah. So,
Wait. Yes, no, can you say something?
Can you hear me?
Yeah, now it's okay, sorry.
Okay, so again, when we have these matrices, the Lyapunov, let's say, equations, we can of course solve them offline. We need to know the information about the system and all these things. But the idea on this one was that I want to solve everything online without any information about the system. And because, you know, for example, system can change, or let's say you have an airplane where actually burns fuel, so then your mass changes. So whatever you have computed on your computer before and you put it into your system is not optimal anymore because your system dynamics change. So what we want to do is we want to converge to the solution of these Lyapunov equations in real time without ever solving these equations.
Yeah, okay. But what is the data requirements to actually do that? I mean, there's lots of data needed, I think.
Yeah. So for the first part, what we do, we just measure the state trajectories. And the second part is we do output feedback. So we just measure our output and we know what we put in the previous input. So in the first part, we want to do the data needed is the state trajectories and the control inputs. And the second part of the talk, where the discrete time systems are output and inputs.
Yeah. Okay, great. Any questions in the meantime here? Online, anyone? Well, if not, I have a final question.
Sure.
Um, how is technique used in social systems, social technical systems, or economic systems? I mean, do you know that? I mean, in control theory, in those areas, I mean, because it seems to be applicable, right?
Yes. I mean, that's actually a good question. So, control theory can be applied in social networks and social influence, so by using distributed control algorithms. So we have applied actually reinforcement learning in social networks, but in these specific techniques that I talked here about actuator and sensor placement, maybe you can place, I don't know, more influential people around in social networks or things like that. I mean, yeah.
Okay. Yeah. Okay. Well, thank you very much.
Thank you very much, everybody. I really appreciate your time. Thank you for coming to the talk. And I'm looking forward to interacting with you in the future or any conferences.
Yeah, that would be nice because I'm going regularly to Atlanta. Actually, I have a contact.
Every time you come in Atlanta, please shoot me an email, and then I'll be happy to host you. And then you give a seminar, and then we can talk.
I'll be there in May, so I'll contact you. Thank you very much. There's a question. Sorry.
Oh, yeah.
Yeah, hi. It took me a while to see the question. In the examples, the sets of actuator sensors were not very large, let's say 20. Does this scale to very large pools of possible sensor actuators? Is there a limit?
Yes, actually, it scales. I think in our papers we have larger systems. So yeah, it scales a lot. Yeah, actually, that's why I put a remark that they're very promising for large scale systems. They're actually very fast. Yeah.
Okay, thank you.
Yeah, but I will be happy if you can send me an email. I'll be happy to share some papers with you if you want to.
Oh, great. Yeah, thank you.
Okay, well, we said goodbye already, but let's do it again. Thank you very much.
Thank you, guys. Thank you very much for everything. Thank you.
Bye-bye.
Bye.
Bye.